Let's talk about deductive databases. So who knows what a mangle is? A mangle is this old-fashioned device that people used to use before there were washing machines. So they washed laundry in buckets of water, and then they rinsed it, and then in order to get the water out and have a like ironing effect, they put it through these two rollers, and there's like this crank, so it was a hand-operated machine. And I'll tell you a story, and it's the story of centered around deductive databases, that is around cleaning data, right? There's some analogy here, and it plays on many levels. So we zoom out from the very concrete sort of imperative programming style to a more declarative paradigm. But before we do that, I want to start from a very high level, right? Like a long time ago, Peter Nauer wrote this essay that is programming as theory building, where, like, in the light of recent industry trends, it's like helpful to remember that there is an alternative view to the predominant and often repeated view that programming is about producing artifacts. So many people believe that writing software is about writing code or documents or things like that. And but there are several things that actually aren't really captured by that. And that is something that is not so obvious often, and it often gets rediscovered. But it's like programming as producing artifacts doesn't really capture many things. So in his essay, Peter Nauer wrote about this, that like the theory of a program is what he advances. Theory here means not like a formal theory, not like Greek letters and horizontal bars, but it's what people understand. Like why are the abstractions written that way? Why have the trade-offs been done like that? And why is the program the way it is? Like what has produced these artifacts? And he's writing about this knowledge being essentially in people's heads. And it so happens that when the team gets disbanded and the software is still used, that the software is dead, right? It's no longer alive, right? Like, and it can be revived by people going there and understanding again and reconstructing the motivations and the thoughts that went into the software. And that, in my experience, that explains a whole lot more what makes systems successful, what makes teams successful, and what makes software really alive. You know, I have some random diagrams here that are supposed to convey that the modern, as time passed since 1985, things have got more and more complex. So there's a lot more things to understand, and you have to work with a lot more people, and you have there are a lot more layers that one has to keep in one's head. And it would be really nice if that knowledge and understanding was not in people's heads, but that we could actually make that explicit and easier to grasp. So I want to zoom in now back to the more to the topic of this talk, which is about databases and data modeling. So data modeling is one place where the model and where these decisions sort of manifest. Like when we make our data structures, we make some decisions, and they end up being the way it is through some thinking. And we don't see the thinking, we see the data structures, right? Or we see the schema definitions, and the database has a bunch of tables. And for a while, all of that is fine, but at some point, software needs to evolve, right? Something changes. There's new kinds of data, or the existing data is different. Especially if it's a successful system that is operating for years, then things are going to change in the world, and you'll have to want to change your data definitions. And what then happens is that in order to change systems and involve them in an incremental way, you need to change a whole bunch of stuff. You don't just change the schema and things carry on. You need to understand the entire rest of the program and how things hang together and sort of like pipe through the data all the way through the stack in order to make the system evolve to handle this new kind of data. And with respect to static checking, that's very interesting, right? Because on the one hand, we like schema definitions, we like type definitions, But at the time that these forces come that require making a change through these layers, then suddenly these things get in the way, because like we are able to evolve our model and understanding of the world. We're like, I can do it like this and I can adapt that. But we have to go through the bureaucracy and changing all the type definitions in the program. So that's a very clear indication that our mental models sometimes can be advanced and sort of further on than what is in the code, and that makes these changes kind of difficult. So that brings me to Mangle Datalog. Mangle Datalog is an open source project. It was born in the context of an actual project that later on. So it was a prototype to in the cybersecurity context. We wanted to visualize metadata that talks about log processing pipelines, but I'm not going to talk an awful lot about that. The key point is we didn't know what data models we would have. We knew that there would be data models, but the data models didn't yet exist. So we wanted to prototype anyway, because this was essentially like a joint 20% project of a number of very talented engineers that I'd like to acknowledge their work. That's not about the data log, but about the front ends that showed these things, which was internally recognized, and it's used by hundreds of people every day. So it was very successful. And I think, I'd like to think that our approach to data was part of this success. And that's why I think it's worth that everyone should know about this, and everyone should could benefit and replicate this approach to data outside of this particular project. But for that, you need to know Datalog. So who knows Datalog? All right, so many people know Datalog. That is great. So I've added a few slides to sort of like show the gist of it, but so most of you already know this stuff. Datalog has you know that Datalog has seen quite the resurgence. So it gets essentially rediscovered every year or every couple of years, and the frequency at which it gets rediscovered is sort of increasing, right? Like because Datalog actually comes out of the as you know, right? You said you know, like the Prolog out of the Prolog, a subset of Prolog, like being applied to data operations, but it's so much more than that, right? So briefly, we can model our facts. Our facts are like like a as if I had a subject, predicate, object structure. But or as if I took my relational tables and I took the table name and I prefixed that, and I get these tuples. So essentially our facts are tuples with a name attached to them. And Mangle Datalog adds structured data. This has also been done many times, like to add data structures that are more than just basic atomic types. You can actually have lists and records and those kind of things, maps. And that helps meeting the data where it is. So we can write up data. Then come the rules, right? I'm not going to dwell on this a lot, but you know that if you have facts, you can also have atoms, which are like a predicate applied not just to basic data types, but they can have variables. If you have variables, you can define matching, and if you can define matching, you can define what a rule is. So a rule takes one of two forms. Either it just states a fact. Can you see my pointer? Yes. So this one just says this fact is true, and then we have declared this tuple. We have summoned this tuple into existence, and that alone, by the way, is very useful, right? Like if you think of configuration files, there's many situations in programming where you just want to state the data literally, and many programming languages don't do that. You can build up objects, or you can like put some numbers there, but structured, checked data definitions are not a thing. Like people send around JSON or something like that. That is not what we want. We would like to have static checking, and we would like to sort of take data seriously. And then come the second form of the rules where you have the right-hand side. It reads from right to left, right? Like so if all the goals on the right-hand side match, then you create a new fact that is specified on the left-hand side. So in the example, we have like some facts, and then we can make a rule that says, like, if I have an author fact and I have a book fact, and then here I have like the R is matching this record here, and then I can like match the fields. If all of that is true, then I can just simply extract the information in these facts into a new fact, which is called author, year, and title. So this is like an interesting, the interesting thing is now that this rule, right, like it's at the same time it's a transformation. We take data in one form, we turn it into another form. But so in transformation, we would think of it as a process, right, as a program that gets executed. But it's also declarative, right? Like it doesn't really say which of these things we consult before. Do we first look into the author table or do we first look into the book table? There is some implicit dependency, right? We need this R here in order to extract the fields out of it. But which of these let's say, tables we query, that is not in there. And that is the real power of this paradigm, right? Like that is declarative. It leaves open how we want to execute this, and that gives us the possibility to execute things in a different way. For example, to apply database optimizations. But we'll get to that in a second. So then this very declarative style, it kind of it enables us to give the definition, like the semantics of Datalog in very few words, right? We just say the semantics of a Datalog program is the fixed point computation, right? It's like we start with the naive algorithm, starts with the initial facts, and then it iterates the rules. And you can see from the movement of my hand that this is a little bit like pulling the crank on the Mangle. And we get our data into the form we want. We do not need to really care about the order in which rules are applied and whether they are represented in memory or on disk or what happens, like how. It just is a very abstract, high-level description of what we want. And the names for this, right, the extensional DB is like the things often you start with a given amount of facts, which is maybe your existing configuration files or database tables or things that were declared inline. And then the rules turn this database into a larger database that has more facts. So this again to highlight, right, this very high-level spec. This is an operational semantics, right? But it's not really about the algorithm. What matters is the result of the algorithm, and we can get to the same result in a different way. And just a brief, it needs to be said. Like I've said it like for historical reasons. Like we see Datalog as a subset of Prolog. But maybe that's the wrong perspective, right? Like maybe the Datalog is actually the thing that is more fundamental, more widely applicable, more useful as the basis for extension in all sorts of things than Prolog ever will be. Because Prolog is a full programming language. It specifies that there has to be top-down resolution. Of course, it's Turing complete. You can do a lot of stuff. But the real shortcomings of Prolog from an abstract point of view is that the negation in Prolog is not logical, right? Negation is actually imposing an order, so that gives all sorts of problems. So if you write your goals in a slightly different way, your program may not terminate because you have to really know the order in which the rules are evaluated, and that makes it terrible. So some folks like Girard famously said that he finds Prolog vulgar, right? That it's a vulgar programming language, that it's not logic. And this is the point, right? Like in logic, this is not, there has to be a clear meaning. And in Datalog, we'll get to it, there's a very easy way to define negation, and it's very easy to understand, and no one will object to this. And then this what I mentioned earlier, right? Like we call this top-down or bottom-up evaluation, or they used to call this forward chaining or backward chaining in artificial intelligence, right? Like whether you start from a given end goal, like, and then you go and check the rules whether it is possible to derive this. This is top-down evaluation, or bottom-up is like what I specified earlier. You start from a given set of facts and then you derive all consequences. And the special thing about bottom-up evaluation is that all the theory that went into database optimization applies here, right? Like you can have hash joins, you can sort of like do batch processing of large things ahead of time, and that enables like a lot of efficient ways of computing the consequence of the facts. Which in Prolog is often available as an implementation detail, but it's not really, like it's a property of the Prolog implementation whether it gives you that, whereas in Datalog this is, we are free to do this as part of that declarative nature. So then I promised I would talk about negation. So negation, right, like we can take our program and we can split it and say like a negated atom is a very useful query. It says I tried to find something in this table and I couldn't. That's a very easy semantics. It's not controversial at all. But for that, the table has to be fully computed. So I can take if I can take a Datalog program and I can sort of logically separate it into slices, then after a slice is fully computed, there is the database, and then if the result is in the database, then the negated atom will fail, right? You won't be able to match it. But if it is not in the database, then the negated atom will match. And this is called stratification, and stratification is really easy to understand. I'll briefly mention that now what's so attractive about Datalog is that like in recent years many people talk about knowledge graphs, right? Like about like semantics, like you want to represent facts about the world in an arbitrary, extensible manner, then graphs are very nice for that. But the problem with most approaches to knowledge graph, or if anyone remembers the semantic web, right, is that all those graphs are binary. But here we have arbitrary relations, right? We can have n things lined up in a tuple, and we can express very powerful interconnections that way. And Datalog supports recursion out of the box, so you can have transitive queries. You know all of this, right? Like, but that together means you can impose a graph view on sort of the things, no matter how you model them, and that is very powerful. And sort of across the stack, it's possible to, through articulating these rules, like have very powerful views on the same data. I won't go too much into the examples of static analysis, but of course Datalog is a way to teach static analysis, right? The simple classic data flow analyses that happen in compilers are easily expressed in Datalog. Here's the example of live variables, right? Like there's like definitions and there's uses, and the information flows backwards, right? Like so if I have a graph, which is a control flow graph, and some of the nodes, they can declare variables and some use variables, I can say which blocks define and use variables. And if I have a use, well, the variable is live. And if a variable is live in a successor, so this is a successor, right? Like this edge, these two facts together say that the variable is live in a successor, and my current block does not define the variable, then it's also live in this block. So that kind of expresses that this flows backwards. And if you know the Dragon book, right? Like its more recent edition actually has a nice chapter on Datalog. So it's kind of slowly permeating sort of the word that maybe Datalog is a better way to think about these things, an easier and much more direct way to express logical facts about graphs, and we can use these things for static analysis. And a recent example is the Polonius model for the Rust borrow checker. I have to say it's not a complete explanation of the borrow checker, but it does express the rules, right? So the compiler is accumulating a bunch of information about variables and about the kind of conditions that they have on regions of memory. But we can feed this information into Datalog rules, and then the Datalog rules will be checked at every program point. It will check that the information is sort of consistent, and if there's no error, then we know that there are no borrow checking problems. And that's, again, right, like we were talking about the theory of a program, right, like about like the understanding. We can capture the understanding of what borrow checking is by simple rules, and that is a very powerful approach. Now when I talk about Mangle, that was all Datalog, right? There was no Mangle yet in all of this, except maybe the structured data. So there's a lot of things I could that are in Mangle that you know, like we want to have because there's a lot of things that the modern programming languages should bring. So there's a module system and things like that. But I just want to highlight the key idea. The key idea is that in Datalog is of course very restricted. So all you can do is these fact consequences, but from time to time it would be really nice to do some transformations that are maybe no longer declarative. Like, so you want to essentially generalize the paradigm to be able to do more programming. And a lot of the publications of recent years that use Datalog as a basis of programming language, they do this, right? It's all about using this very expressive paradigm in the context of a general purpose programming language? Well, we start differently. Like I was talking about taking a program and slicing it into these layers. What if we, not before or after or around the fixed point computation, but in the middle of the fixed point computation, at these points where we logically fully computed our relations, what if after those things we inserted a bit of general purpose computation, and then we let the next stage of the Datalog program continue and do its fixed point computation? How far can we get with that, and what kind of expressivity does that buy us? And to my knowledge, so I've read a few papers, to my knowledge, I haven't seen an approach like this, but there have been many approaches that took Datalog, so I would not be surprised if somebody had done that sort of 10 years ago or 20 years ago, so it's really been around for a long time. But it has been working for us, and I'm going to show some examples. So the easiest example is aggregation, right? Like people use SQL for databases, and SQL is not just relational calculus, it also adds aggregation. So for aggregation, you fully compute some table, and then you have a sort of result relation that has like everything. And now you want to fold over that, right? You want to summarize things. Like in this example, we have a project, and it has assigned some developers with some hours, and if I want to sum up all the hours like I want to know how many developers are on a project and how many hours in total are assigned, like I can express that like this. So this same idea of like first a Datalog program is evaluated, it produces some intermediary result, and then we can run this aggregation on that. Like that, I find it's even though it's no longer pure Datalog, it's very easy to understand how it blends with the rest. And maybe the syntax takes a bit of time to get used to, but I guess it's still better than the SQL syntax. This is, by the way, very related to how MapReduce works, right? Like you first compute a large result relation, and then you group the keys that are processed together, and then the reduction phase like turns the list of results that are for one key into a summary. And this thing after the pipe operator essentially says how to summarize. So that's one example, right? We've taken Datalog, very simple, and we've extended it, and still we have these termination properties, right? Like we don't need to care about the order in which if there were multiple goals, right? We wouldn't care about the order in which they are written. We don't really have to care about what comes first. We still declaratively specified what's supposed to happen. Next thing is functions. So if you just add functions to Datalog, then most of these properties like break. Like then Datalog no longer is Datalog, for example, you can have this non-termination, right? You can say I have a piano fact, which is like a 0, and then I just add successors, and this will just not produce any fixed point, because in every iteration, like however you want to evaluate it, like this thing says just iterate and iterate and iterate, and there's no end to it. So that is obviously not the way to go. I mean, if you do this, you really have to know what you're doing, and you're back to full programming. You have to know something about the control flow and sort of like how many of these facts you have generated. You have generated too many facts, essentially. So that's the question. And could we actually find ways to add functions, like things that generate new forms of data, new facts, but still, like knowing that we're in the middle of this fixed point computation, still do that in a way that preserves some of the declarative nature, and that still guarantees termination. So one example we have is the custom lattice join. So you could kind of say, like these rules, they generate facts, and then we have these sets of facts, and if we have more, like there's a natural join, like a lattice join operation is just to make the union of them. But what if I don't want all the tuples? What if I find a good fact or a better fact, I want to remove like the old fact? And that's like as if we would define a lattice with a custom join operation, where the easy example is the shortest paths, right? Shortest path is not something you can express in Datalog, but you can express in Mangle. So essentially, you have, you either have an edge or you extend an existing shortest path with an edge. But if you then found a path, if you found two paths that are the same, they have the same start and end point, and you find that one of them is shorter, just pick the one. And the way we do this is like so this is one example of things that are very expressive that you can insert into this data log computation. And it will not jeopardize termination. If the original thing terminates but had too many tuples, the updated thing will also terminate, and it will have less tuples and will be more efficient. So the way we declare this is to say, hey, there's this merge predicate, and after we've computed the like one iteration of the iterative fixed point computation, we will actually go and call these things and then have like the tuples. We will call this merge predicate. So it's like a computation inside the computation where we check what are the lengths of these paths, and can we actually, if we can call this and this predicate produces a shorter fact, that's a signal for us to say, okay, we can delete the other one. And the implementation will actually delete the tuple. Yes, question?
Couldn't this lead to non-monotonic reasoning if you are able to remove a fact from the database? So say I later query exactly whether or not a longer path exists, but we've used this mechanism to remove that longer path and the shorter path existed. Doesn't that kind of violate the declarative property that you want from data log?
Yes, absolutely. And the reason this works here is that we don't actually go and update. It's not as if like the entire thing is considered, right? We produce a new iteration in the iterative fixed point computation. Then we check for the new things, we check whether there are existing things. So there's like, we don't go and delete, but yes, like you cannot decide for rules whether they are non-monotonic, and it's, so in this case it works, and we don't really, like this custom lattice join is very restrictive in a sense, so I don't think you could get into this, but of course in general, you cannot, there's no way to decide the monotonicity of the rules, so if you had a more general way to do this, then you could write these non-monotonic programs. Like I think in Soufflé is the same trouble. So I believe in this case we would be monotonic because after the iteration is done, the existing stuff prevails. But like maybe for other more general ways of doing these custom lattice joins, we might get into this problem. But I don't think we support them right now. So getting back to how to handle data, like a general approach to handle data, right? Like this syntax of having facts, like with maybe some input and some output predicates, that is also, that's a very uniform way to access any source of data. And you could imagine any sort of computation or querying external data sources to take the very same syntax. So there's an external predicates API where we could like say, okay, we make an RPC to some backend, and we give it these input things, and then back come these output variables, and that can be then configured through mode declarations. But apart from external backends, I mean, you could really think of any sort of computation that you can expose as these kind of tuples. You can express them with the same syntax. Of course, then, like there is this, what I mentioned earlier, there's some dependencies, right? If mode declaration says some of your inputs have to be there before. So while it's true that the order doesn't matter, if you declare something as having an input mode, that means, okay, like some other goals have to happen first so that I have all the inputs, and only then I can actually run this external predicate, let's say, and produce the output variables. So as I said, there is an actual system that works this way, and this uniformity, it goes a long way, right? Like, so we had we found a need to have these data log evaluations at build time, because there's static information, there's like configuration files, or there's like stuff that the build system knows. We pull the crank, we evaluate, and we get our facts. Then we push these facts into our production environment, where there's like more data available, right? Like, so we evaluate again, and we access external data, and we get more facts. And because that's not enough, right? Our users may have other ideas of what things they want to query for. We also let them write queries, which are Datalog programs, and then we sort of incrementally taking the existing intentional database as a new baseline, right? Like we pull the crank again, and we do another data evaluation, and we return the results that the user requested. So this, I don't have a name for this, I'm happy to take suggestions, but the fact that the same sort of kind of computation happens across all the layers in different environments, this is something that you don't find all that much, right? Like in a traditional three-tier application, right? Like the database does something, and then the middle layer does something, and then on the front end things happen, but they're all different. They use different languages, they use different patterns, they use different abstractions, and it's very annoying because that is what is difficult to change, right? That requires knowing many different things if you want to go across the whole stack, whereas this one is the same thing across the stack, the very same thing, and it's very flexible. And we have a form of static checking that I didn't go into. So what does static checking mean in Mangle Datalog? So it means that we can, through type information, sort of like tell, if you wrote a query that can't return any results, we tell you, right? You probably have made a mistake. I briefly want to zoom out again and see how this could apply to cybersecurity. This is not the system that is implemented, but it was the thing that led me to investigating query languages. And let's see what you think of this. So in cybersecurity, you have to deal with information and event management. It really starts with knowing what you are protecting, actually. What is protected, what is worthy of protection, what is actually happening. And so people write these log processing systems, and they essentially take the non-contextual information and they try to curate and select and add annotate and enrich information, which can take many forms. Like you can have classification, but the forms can also, they can be false positives and all sorts of things, right? And there can be legitimately different ways to use the same, to view the same data. And to have a system that supports that, right? Like with Datalog, it becomes very easy because you just define facts. And these facts could come from the logs. You presented the logs in this view where the relevant things are. It could also be abstractions, right? That maybe there's like rules that produce these facts. We don't need to know. We can talk about these things like in a very abstract way. And we can talk about the patterns in an abstract way, right? Like we can define sort of patterns that we want to recognize by using the very same rule mechanism to express time series patterns, or like a privilege escalation, which is like when a process starts, when the parent process was not an admin, the child process was an admin had admin privileges. That is, then apparently there's something going on here which is worth checking. And finally, we can compose the rules, and that is really something you should take away, right? Like Datalog allows you to compose queries, which other query mechanisms and formalisms don't do. And so like everything comes together. If out of little building blocks we can build ever more building blocks, and it's all explicit. Like you can just look at the rules, and without knowing sort of what is going on in detail, like maybe this is a rule, maybe this is a log, right? Maybe it's an intermediary stored snapshot from last week. You can build like whole systems out of, and that's a way to tame the complexity. So to summarize, like what have we done actually here, right? Like I'm sure there are many ways. There are going to be many more languages based on Datalog. We have, like what I've wanted to highlight is that the declarative paradigm helps us to make things explicit, right? We can look at these rules, and the rules give us abstraction, right? We do not need to know. If we don't want to know, we do not need to know whether an atom on the right-hand side of a rule, where it actually comes from. But if we want to know, we can go and we can look up whether there are rules or whether it's an external thing, and we can drill deeper. but we don't have to, right? Like which is different in an imperative program with many data structures and mutation. So the uniformity has helped us like give us maximal extensibility, right? Like it's extensibility with respect to data. You can add new forms of data. You can add new forms of rules. You can test your rules, right? Like, and you didn't necessarily need to know all this stuff ahead of time, as we didn't know our data model when we started. We were just able to change it along the way. And finally, like there are things, this expressivity that with few symbols you can express a lot of things, and the modularity that you can have things like packages and imports, which I didn't show. These things matter to humans, right? Like it's like many people talk about sort of like code being generated by generative AI and whatnot. But ultimately, if you want to be responsible for something, you need to be able to understand it, and you need to be able to understand it quickly. And then all these things that you know, we like this hard-earned knowledge of programming languages, that modularity and good abstractions and good APIs matter. All these things are still true, and we need, like in my opinion, we need approaches like this that really focus on the data, right? Like not just on the computation, but how we do this with data definitions. That was what I wanted to show, and in our case, it worked very well. And I hope that you'll be able to use this in your own systems to maybe replicate and use a bit of Datalog to make the world a better place.
We do have time for maybe one or two questions real quickly.
Thank you. As you know, I'm a big fan of Datalog, and I'm using Souffle currently. So I saw the operator that you want to add about for lattices, and Souffle, yeah, the semi-join. Yes. So Souffle has the subsumption construct that does something similar, but it's very nice and expressive, but there are two things with it. One is it complicates implementation, but let's leave that aside. We also have never used it fruitfully. It slows down like normal computation quite a bit, at least by a factor of 2, because every rule that might have results being subsumed needs to check before it produces new results. So do you have any ideas of how we can actually do something like custom lattices with virtually zero overhead?
That's an implementation question. I didn't expect those, but it's so the question was you were on the microphone, right? Like to repeat my understanding of the question, how to actually make this fast, right? Like have this expressive way of dealing with the mutations to the set of tuples you want to compute while not spending too much overhead. I think the key here in our system, so our system is very simple, right? Like we do all sorts of stuff in memory. In memory, things get very easy because memory is fast. But even so, like we had to tackle performance issues, and there are small things that make a big difference, right? Which is like indexing, like just like in databases. So if you're gonna to check whether your subsumption holds, right? Like you're going to make some computation. To make that computation fast, I mean, maybe you want to do other lookups and whatnot. If those lookups are fast, then the subsumption can be faster. So it's not a fundamental algorithmic answer, but it's just sort of like the constant overhead that is a big deal, right? Like by using the right representation and using the right index, querying the right columns, like we were able to find like big speed ups, and they were enough for us. If you ask me about the algorithmics, I don't really have a great answer for you. I think the thing I'm working on a Rust implementation of this, which is supposed to be more than just in memory, so it should actually go to disk or to you know, like more scalable media for intermediary results. And I think the key is going to be as you get more and more facts, right? Like how you organize your data. Like a columnar representation, for example, will mean that you know you can do your batch computation differently. So I think you still have to do the amount of work. You have to find the tuples that are relevant, right? But for example, like Souffle has the equivalence relation. I guess that's a good example. If you know that your relation is symmetric, transitive, and reflexive, why don't you make a data structure that actually represents those things efficiently? And I know from my colleagues who use Souffle that Souffle is not great at sort of bring your own data structure things. In Mangle, there's a fact store interface, you can just implement it. So if you have an equivalence relation, like you can actually build a fact store that will respond to queries like very quickly, and maybe it's backed up by a union find algorithm, and that way, like you can, that can have a major impact on the sort of the complexity, because you have to do less work. It's no longer linear scans, but maybe, you know, you have like a reduction and you have log complexity to find your things. And I believe that's the key, right? So there's that sort of extensibility where you can choose how to represent your relations. I haven't thought much about how to represent the lookups for the custom lattice joint, but I suspect one could do something like this, where by making that configurable, you know your domain problem and you will be able to pick the implementation that works best. So that would be my answer.
Okay, so this concludes the session. So we'll see you after lunch, but let's thank the speaker.